Imagine a world where the problems that baffle our most powerful supercomputers. I'm talking about things like designing new drugs or optimizing global supply chains get solved.
Not in years, but in seconds.
In seconds.
Yeah.
Exactly. And, this isn't sci-fi anymore. This is a rapidly approaching reality, all thanks to quantum computing.
Mm-hmm.
So if you've been trying to get your head around how this all works without, needing a PhD in physics, you are definitely in the right place.
Absolutely. Our mission today is really to give you the shortcut. We've gone through the research to distill the absolute essence of quantum computing.
So the fundamentals.
The fundamentals, yeah.
Yeah.
What makes it so powerful, the big breakthroughs we're seeing right now in 2025, and the critical hurdles we still have to get over.
Okay, let's unpack this. To really get the scale of this quantum leap, I think we have to start with what we all use every day. Classical computers.
Right. The simple binary system.
The bit. It's just like a light switch, isn't it? It's either on, a 1, or it's off, a 0. And that's it. That's the limit.
And that on or off limitation means everything gets processed sequentially, linearly. Don't get me wrong, it's incredibly fast, but you hit a wall.
An intractable wall.
Exactly. When a problem's possible solutions grow exponentially, that one-by-one processing time can quickly exceed the age of the universe.
Which brings us to the concept that changes everything. The qubit.
Mm-hmm.
So unlike that light switch, the qubit can exist in a state of superposition. The best analogy I saw was a spinning coin.
Yeah, that's a good one.
It's not just heads or tails.
Yeah.
While it's spinning, it's kind of representing both 0 and 1 at the same time.
And that ability to hold multiple states at once is the absolute key. It lets a quantum computer explore all these different paths in parallel.
So instead of 1 by 1,
it checks them all at once.
Okay, so if superposition is this powerful multitasking, then the second piece, entanglement, is like the network that connects it all.
That's a good way to think about it.
I had to read this part a few times. Why did Einstein call it spooky action at a distance?
Well, because it's spooky. It breaks our common sense idea of how the world works. Entanglement is when you link two or more qubits and they become inextricably connected.
No matter how far apart they are.
Doesn't matter, across the room or across the galaxy. If you measure the state of one, you instantly know the state of its partner. It's a correlation that classical physics just can't explain.
And when you put those two things together, superposition and entanglement, that's where you get this aha.
That's where you get exponential scaling.
Right. Classical computing is linear, double the bits, you double the power.
But with quantum, it explodes. If you have a qubits, you can represent $2 to the power of nice states, all at the same time. And that growth is, well, it's hard to wrap your head around.
To put that into perspective, there's this one number, 300.
300 qubits, yeah.
Our sources confirm that if you could build a stable system with just 300 qubits, it would hold more computational states than there are atoms in the known universe.
Just think about that for a second.
It's a mechanism that scales in a way humans have just never built before.
And that scale is exactly why we need it. Classical computers just fall over when they try to simulate complex systems where everything affects everything else.
And this brings us right to why this actually matters to you, to all of us. Let's talk applications like drug discovery.
A perfect example. Right now, figuring out how a complex protein will fold or how a new drug molecule will behave, it takes a huge amount of supercomputer time. Months, even.
And a lot of guesswork.
A lot of guesswork. But with quantum simulation, you can model those molecular interactions at a fundamental quantum level.
Accurately.
So months become
hours, maybe days. This isn't just speeding things up. It's a total paradigm shift for pharmaceutical R&D. It could bring life-saving medicines to us years faster.
That's a huge insight right there. And it's not just medicine, it's finance, materials, science.
Imagine designing a portfolio where you can weigh every possible market variable at once. Or designing a new type of battery from the atom up that has tripled the capacity of what we have now, if we connect this to the bigger picture.
The utility of that kind of optimization is just massive. Think about global logistics. Finding the most efficient route for millions of deliveries at once
means less fuel, lower emissions.
Far beyond what today's software can do. It even moves climate modeling from broad estimation to fine-grained precision. simulating the entire atmosphere, molecule by molecule.
Here's where it gets really interesting, because this isn't just theory anymore. This potential is becoming tangible. We are seeing real breakthroughs now in 2025.
The progress in hardware is just astonishing, and we're seeing a few different philosophies emerge. You have superconducting systems like Google and IBM are building.
Right.
Then there are trapped ion systems and topological ones, which is Microsoft's bet.
Let's stick with the big players. Google's Willow chip made huge waves. The sources said it operated, 13,000 times faster than a supercomputer?
On a very specific custom-built problem, yes. And that's a crucial distinction we have to make. That experiment showed quantum advantage. It proved, that the quantum math works faster. The bigger debate is over quantum supremacy.
And supremacy is?
That's the point where a quantum computer solves a genuinely useful, real-world problem faster than any classical machine could.
So we've proven the engine works, but we haven't won the big race with it yet.
That's a great way of putting it. But that's what everyone is pushing for.
And the competition is fierce. IBM is making some bold claims.
Very bold. They're aiming for that verified advantage by 2026, and they're talking about achieving fault-tolerant computing by 2029.
What does that mean exactly? Fault-tolerant. It sounds important.
It is the holy grail. It means the machine is robust enough to run long, complex calculations without the inherent fragility of the qubits causing errors that wreck the whole thing. It means your error correction actually works reliably.
Which is very different from Microsoft's approach with their Majorana 1 system. They're using topological qubits.
Why? It's all about stability. Instead of just trying to manage the errors after they happen, they're trying to build qubits that are inherently more resilient to begin with.
So fewer qubits, but better quality ones.
That's the idea. They're hoping to leapfrog some of the massive error correction challenges that the other guys are facing.
And we're already seeing this pay off in the near term. Experts like Dr. Vasquez are confirming that even today's noisy machines are helping with things like supply chain optimization and early drug screening.
Yes, they're already proving useful. But that tangible progress forces us to confront the technical reality. The quantum realm is still full of immense challenges, the biggest one being decoherence.
Right, decoherence. It sounds like something that happens when you spill coffee on your laptop.
Yeah, but it's about 1,000,000 times more delicate than that.
I can imagine. Qubits are just unbelievably fragile. They lose their quantum state. They stop spinning, to use our analogy, from the tiniest disturbance, a little bit of heat, a stray vibration, an electromagnetic field.
And it all just collapses. It all collapses. That's why these machines have to be kept in these incredibly controlled environments, often cooled to near absolute zero.
So the engineering is just as big a challenge as the physics.
Precisely. You need perfect vacuums, perfect shielding. But the good news is we are getting much better at fighting it. New error correction methods are letting qubits stay stable 15 times longer than just a couple of years ago.
So while the engineers are tackling decoherence, there's this other huge implication we have to face: the quantum threat.
This is the thing that keeps cybersecurity experts up at night, and for good reason.
Why?
A large, stable quantum computer running something called Shor's algorithm could, in theory, break most of the public key encryption we use today.
So the stuff that protects our bank accounts, our emails, national security?
All of it. The RSA and ECC standards that the entire digital world is built on.
Okay, so if quantum can break the internet's lock, what's the key to fix it?
The fix is a race. It's a race to develop and deploy post-quantum cryptography, or PQC. Essentially, yes. New algorithms that are designed from the ground up to be safe from both classical and quantum computers. We have to deploy the defense before the weapon is fully built.
And beyond the technical threats, we have to start thinking about the societal impact of this, don't we? Especially given the kind of infrastructure this requires.
Absolutely. The ethical questions are paramount. We're not talking about a new chip for your laptop. We're talking about massive, expensive, specialized facilities.
With cryogenic cooling and all the rest.
Exactly. So who gets access to that power? That's a huge question.
So what does this all mean? We started with a simple on-off of classical bits. We journeyed through the weirdness of superposition and entanglement, and we saw the insane potential inside just 300 qubits.
Mm-hmm.
We have real, verified progress on the hardware, and we're actively fighting the big challenges, decoherence and the security threat.
And the ultimate goal is still out there, solving these intractable problems. Personalized medicine that actually works, clean energy from optimized fusion, precise climate interventions.
Right.
The debate over supremacy versus advantage will go on, but the move toward genuine practical utility, That's undeniable now. We're getting very close to solving real-world problems faster with these machines. And that leads to a final provocative thought for you to consider, building on those resource concerns.
Okay.
If a few hundred qubits can manage more states than atoms in the universe, and that power requires immense, specialized, and geographically concentrated infrastructure, these giant supercooled centers, how should we, as a global community, ensure that access to this exponentially powerful problem-solving tool is distributed fairly? How do we stop it from just deepening the technological and economic divides that already exist? It's a question that goes way beyond physics and into global governance.